This is the Whirlybird Pitch Parameter Optimization Project from Tyler Kropp, Ryan Bratt, and KK Shumway in Dr. Hedengren's Process Control class. The objective of our project was to find the correct control parameters for the Whirlybird lab model simulation, specifically pitch, which is angle of elevation from the floor. As you can see in the left, it starts at 0 and will raise up to some set point. The Whirlybird in physical form consists of a drone and a weight mounted on a lever. This form has been adapted into a MATLAB-based model that correctly predicts the physical responses of this system. We took that MATLAB model and copied it into Python and sought to find parameters optimized using scipy.minimize. We found parameters that included no penalty for overshoot, as well as one that included penalty for overshoot.
Here are the results of our optimization. The red line is the set point. We were moving from a set point of 0, which is horizontal, to an elevated set point of pi/9 radians. The goal was to optimize the PID parameters for the best performance for this specific set point change. The green line is the initial parameters obtained from MATLAB, which you can see moves very slowly. And once we performed our optimization, we got it to reach the set point within about 1 second. You can see in the zoomed in graph, we did an optimization where we allowed overshoot and one where we penalized overshoot. Here is a graph showing time versus the fan speed. You can see that the controller adjusts the fan speed differently when using different optimized PID parameters. In our optimization process, we performed sensitivity analysis. This shows KC. This shows absolute integral error as a function of KC, and we combined this with scipy.minimize and observing this graph to get close to whatever we thought was the best solution for the best performance for this, moving from 0 to pi/9 radians. We also performed sensitivity analysis with penalizing overshoot, which we found that below 99 KC value caused an overshoot.
So here's a table of our final values, and it's interesting to note that the optimized PID parameters without the overshoot penalty actually had a smaller integral absolute error than those with the overshoot penalty, which makes sense because although the one with overshoot penalty produced a smoother curve, you have more integral absolute error within that response. Something else we found that was interesting is that tau I had little effect on the optimized overshoot penalty versus without the overshoot penalty, and so it was pretty much negligible in that response. So we wanted to compare these values back to the original PID parameter values that MATLAB had, and as you can see, the IAE was significantly lower than what the values started at, and so we were able to optimize those with PID optimization. So unfortunately, when we plugged back in our optimized PID parameters into the system, the response was less than favorable, and so we realized that maybe we hadn't copied over the model completely correctly from MATLAB to Python. However, we were able to optimize the Python model that we used. So in conclusion, as shown in our data, we were able to use a scipy.minimize function to minimize integral absolute error and receive the best PID parameters for our system.